what I hope will emerge from the talk, and I was actually saying this to Donica earlier on, is that every time I'm asked to give a talk on Mars and re-engage it, so something I spent many years researching for a book, it's new, it's different. I'm having to remind myself of the nuances and the sophistication of this program and what we're doing there, because it's a planet that we can take for granted. It's a place that we kind of
your X there, you'll take it out. It's just
I don't see it on my screen. Can you see one?
Yeah, I can. Yeah, sorry. It's just
no,
time.
Go for it.
It'll blemish your photographs. Just going to, sorry folks.
Xbox the spot.
Switch. Here we go. I'm just going to temporarily.
No.
Okay, and I'll go back.
No.
Oh, sec. Now I have to put them back again. Sorry.
Not really.
Escape is released.
Give it a minute.
Yes.
Now go back in to the car. Can you saw that thing?
Here we go. Okay, and turn that out. So that's them off your screen. That's right.
And then it's the this one here. Hopefully,
but we want to. I bet you the screens will come out the wrong way around again. Yes, they will. Hold on.
I don't know. Actually,
Sorry about this. Is it? Oh, yeah, it's getting to us. Oh, there we go. Sorry,
No.
I couldn't get the cursor up. There we go now. Swap displays, and we're back.
Brilliant.
That's now gone. Okay.
So, oh yeah, first I should say, by the way, that these 3D glasses, we'll only use them for 4 or 5 images through it. I'll cue you for them, okay? So the vast majority of the images, we won't be using those for it. But the thing about Mars is, as I say, is that it's a planet that we can't take for granted. And it's a planet actually that we give an awful lot of time to, and maybe very often we wonder, why are we doing that? And the first thing I'll say, by the way, is I've set an alarm. Second thing I'll say is, for about a half an hour in, this is a long talk, but I want to get it done in time because I'm finding that I'm struggling to actually get talks done in the time. And that's because even with rehearsal, because they're such big subjects, this might be actually 2 talks. So I want to get through the first half as quick as possible because it's kind of the older part and get towards some of the later findings that we've actually been uncovering in recent times. But however, one of the, I suppose, the areas that I feel is new and a renewal for me when I was developing this talk for IAS this time was a reminder of what this is all about. It's about a search for origins. We're on Mars partially to learn about Mars, but we're there very much to try and understand about the origin of life as well. Now, there are 2 big key, I suppose, domains in modern science: the origin and fate of the universe, the origin and cosmic abundance of life. And we've multiple approaches to those. So in terms of exploring the origin of life, of course, we have an astrophysical dimension to it with many different telescopes that are searching the skies. So we've all heard that the VISTA telescope in ESO just produced a 200,000 image map of the central Milky Way in infrared. This is the Spitzer survey of the Milky Way. This is 1/16 of it, 50,000 images knitted together. But one of the major discoveries in it is that anything that's green in this is organic carbon in space. More than 90% of the carbon that we know in space is organic. And of course, we're detecting protoplanetary disks, solar systems everywhere, over 5,000 exoplanets discovered right now, and more on the way the whole time, with huge programs from ESO, still trawling through Kepler data, and all sorts of new surveys to come online. We're likely to discover tens of thousands of planets in the coming years. And even closer to home, there's 2 other locations that we're very interested in the question of exobiology. Europa and Europa Clipper to launch next month, which will do a very close survey of Europa, and then Enceladus, the moon of Mars, both of which we believe have subsurface oceans that may have contain more water than even Earth, all of Earth's oceans at a temperature, and therefore may harbor life. But before we just step into Mars again, and as I say, this was the I suppose the first thought, I suppose, this wasn't a new thought, I suppose, for this talk, but something I had to keep reminding myself is, what do we mean by the origin of life. What do we mean when we're saying we're searching for the origin of life? We bandy that term around as if it means something that we know. And the fact is that it's a term we don't know, because we don't know the origin of life. None of us, not one person who's ever lived, has been able to uncover what gave rise to life on Earth. Now, we're cracking that nut from those multiple dimensions I mentioned a few minutes ago. And even the notion of, we talk about the Goldilocks region of solar systems. Well, this image very starkly reminds us that that's, of course, a very simplistic view on it. Earth is in the Goldilocks zone, the moon is too, but you couldn't get two different worlds in terms of a question of life. So the origin of life is not a question, it's a label that actually we're figuring out is a stepping stone or a label to a million questions. And we're not even sure we'll ever have that eureka moment where we'll say we've discovered life. But what we are doing over time is building in ever more sophistication into how we're probing that question. And at least some of what we think is associated with life, although it doesn't necessarily have to be this, is that we think it's a planetary phenomenon. So when it comes to a basis for the origin of life on Earth, we're talking about an ancient relationship between the Earth and the life here. That the first cell to originate was actually the end of a previous process, a previous prebiotic chemistry process that involved the actual raw materials of the Earth, that somehow or other gave rise to inanimate matter becoming a celled or a membraned entity filled with water, in which you've got 2 trillion atoms that can self-replicate, metabolize, sense and so forth. So, but the thing is that process from inanimate matter to something as highly organized as a cell is a gargantuan set of steps. And that's really the domain within which the origins of life are pursued. And even amongst that, we can throw around terms like organic synthesis. Where did the organic molecules come from? Even polymerization into nucleotides like DNA, or membranes that give us rise to cells. Even those are hugely complex. To get something like a strand of RNA is not something that you just find in nature. It's beyond complex chemistry. So the actual path to understanding even the subcomponents of life, we're now beginning to realize in the quest for the origin of life are tough questions. We've been doing this seriously now for more than 60 years, and we have not even found those answers to those subsets of subsections of cells. We're not there yet. But nevertheless, we do feel as if, because life arose fairly quickly on Earth, that it's intimately connected to the planet as it was at the time, the resources that were available from nature, and then for those to somehow or other self-organize, come into complex systems and give rise to life. Now, the problem, of course, is that all of that is gone from Earth. It is so self-rejuvenated. And to cut to the chase of really why we're at Mars, and this is the first half of the story, Mars exhibits many of the characteristics of early Earth. And critically, because it shut down its processes about 3 billion years ago, it retains a global record of those early planetary processes that we suspect gave or were at least seriously contributors to the origin of life on Earth. So Mars is of interest because we think if we want to know how life arose on Earth, Mars might give us many of the clues. Again, when I've given this talk, many of you have seen this talk, have seen these slides before, and I apologize for that, but as it was myself and Mick decided jointly we do Mars, and then we realized I had done a talk in 2021 on Mars, but I want to actually almost reinvent or repurpose this slide. I remember when I gave talk last time saying we have a checkered history with Mars, which we do, but however, I want to really say that actually we've had a long journey with Mars. And we're really, I suppose we want to talk about it, we're in the 4th major campaign of trying to understand the planet since Kepler. So Kepler, of course, used Mars and its very eccentric orbit to tell us that Mars orbits the sun and not the Earth. So Mars is the first world that we use to tell us something about ourselves and our place in the universe. Through the 17th and 18th centuries, we had Cassini and Huygens and Herschel analyzing the planet and finding, as you may know, very Earth-like properties from a superficial standpoint: 24-hour day, 24 hours, 37 minutes, 23-degree angle tilt, 4 seasons, polar ice caps that melt in the summer and grow bigger in the winter. So through those centuries, we attributed very Earth-like imprints or senses about what Mars might be as another world. People did question whether there might be life there. And then through the 19th century, we had the aerographers, the great Mars mappers. And what happened really through the 19th century was that the telescopes became what we say diffraction limited, as distinct from atmospheric limited. They became so good that at moments of atmospheric clarity, the telescopes could go beyond what the atmosphere would allow you to see, and we could see fine-grained details on Mars. The problem is, and it is a fascinating era, that when this started in the mid-19th century with maybe 8-inch refractors and ended around 1916 with Percival Lowell with 24-inch refractors, that's two different eras of observation. And what started off as an innocent observation of lineations on the surface, which was an optical illusion, ended up with Percival Lowell, which was really a delusion about the notion that there might be actually ancient aliens on Mars, or maybe even aliens there. Like Percival Lowell was claiming that he was seeing a thing called gemination, whereby on one night you see one canal, look back there, the next night you see two canals. So he was saying some sort of change. He wasn't saying the Martians were alive now, but maybe some sort of transitory event was giving rise to the visibility of different canals. But Schiaparelli never claimed that there was an artificial creation of them. And Schiaparelli, by the way, he was a draftsman. This is the result of months of observations, probably like several years of observations. Plus, he was colorblind on a planet that shows red and green tinges. So maybe the optical illusion he saw might have been all the more heightened. Who knows? There's a fascinating investigation to be done in there, by the way. I think there's a couple of PhDs in the history of astronomy to look at all of those telescopes and find out their optical capabilities, to find out, because Antonadi was seeing this when Percival Lowell was seeing this. And I don't think Percival Lowell was trying to be dishonest. You know, he was probably just trying to convince himself that there was more going on than there was. But you can see some similarity in the actual the symmetry. But the point is that what were the telescopes they were using? How good were they? You know, there's a bit of a debate there. But in any case, nevertheless, I know I'm already spending too long in this earlier part of this talk. The thing is that by the early 20th century, by the turn of the 20th century, a large proportion of the astronomy community felt there may be canals, and a large proportion felt there wasn't. It was a contentious issue. Nevertheless, through the early 20th century, Mars science planetary science even, dropped off the radar. Of the 1,000 professional scientists in the USA around 1920, 1930, only 20 were doing planetary science. And Mars was largely seen as taboo because of the actual canals episode. So it was largely ignored. I should point out there's a paper published by Barnard in 1892 where he actually says that looking at Mars was like looking at the landscape from the top of Mount Hopkins, where he could see ridges and potential mud flows and things like that. So it looks like as if the likes of Antonadi and Barnard were seeing at fleeting moments the kinds of images that we might see with our Hubble images, or when you stack images these days. Very, very good global images of the real features of Mars we're seeing in the late 19th century. Now, cue the 20th century, and of course, planetary science dropped off. But the thing is that we had the revolution in physics and astrophysics for the first of the 20th century. We had the discovery of the expanding universe, therefore an origin to the universe, therefore an origin to life, or to planet Earth, and therefore to the origin of life. So as the 20th century rolled on, scientists start to question about the actual natural idea of life being a natural phenomenon. Joshua Lederberg, who won the Nobel Prize for Medicine in the 1930s for linking microbiology to biochemistry. He made the link, calling of our biochemical basis for life. And he was a colleague of Carl Sagan and Melvin Calvin, who got the Nobel Prize for photosynthesis. They teamed up actually in the late 50s when NASA was forming. And they got together actually with Frank Drake and then the administrator for NASA at the time, James Webb, who was headed for the Apollo program, but also saved planetary science, by the way, as I mentioned in a minute. But they asked the question, could there be life on Mars and Venus? And they proposed the first missions to Mars, the Mariner 4. Now, when Mariner 4, Mariner 6, Mariner 7 got there, they saw craters. And of course, that told people that Mars was dead and dormant. Very low potential for life. NASA recoiled Lyndon B. Johnson wanted to cancel JPL and the planetary science budget. There's the minutes of this meeting were online. I read part of them when I was writing my book in the early noughties. I can't find it now. I think just things have tightened up with the web. But James Webb in a single meeting convinced Lyndon B. Johnson to reverse his decision. And he basically said to him, it was a political argument, we have 30,000 human years of experience in JPL. Are you going to cancel that in the Cold War era when you got all that space advantage? And he convinced Lyndon B. Johnson it was worthwhile continuing with civilian science, and therefore then the Viking and the Voyager and even Hubble may not have been possible without James Webb making that argument. Lyndon B. Johnson reversed the decision and gave us then the 70s and the 80s stuff we're aware of. Now, when Viking went there were orbiters, although that's Mariner 9, although it looks very like Viking orbiter, by the way, they're very similar. So the thing is that when Viking landers went there, they found that the surface was made of an peroxidizing agent that destroys organic matter. And we found no organic matter, so forget about finding microbial life or vegetation. And again, NASA recoiled, and around the late 70s, they decided no more Mars science. In fact, that's why Carl Sagan set up the Planetary Society with Bruce Murray and Lewis Friedman, because they basically felt that the planetary science and NASA space science community recoiled too much from Mars. And Sagan's argument was you can't say something about a planet from having landed in just 2 locations. So they set up the Planetary Society to garner support for space exploration, particularly planetary exploration. But the Mars orbiters had taken 60,000 images. So all through the 80s, while there was no missions to Mars, geomorphologists and geologists and geographers were beavering away on these images and assembled this astounding image. Now, this is actually not the image. There's a very similar image to this, but this is the Mars Mola map from Mars Global Surveyor from around the year 2003. But nevertheless, it's the same map where we suddenly were able to piece together the history of Mars. And what you can see is a great dichotomy. Craters in the base, bottom, flat on the surface, lava plains. The Tharsis Bulge here with the great volcanoes and Olympus Mons. Valles Marineris, a rift valley. The Kazai River, which is as big as the Amazon, water flowed through it for hundreds of millions of years into the Chryse plain, which we now believe was a shallow sea commotion. And then we have the Hellas Basin and the Argyll Basin here. And we saw that Mars actually had a dynamic past that wasn't that much different to Earth. So we found 10,000 dried riverbeds, ancient seas. Argyll was a sea, rivers, tectonic and volcanic activity. And this therefore suggests that Mars was more Earth-like than in the past than it was now. And so in 1995, a document was written called An Exobiological Strategy for Mars. I remember reading it around 1998, and it changed my life. Document. I actually have it on this computer, no photocopy of it. It was mind-blowing to read the thinking about Mars from the top 18 scientists. And Carl Sagan, he was dying. He died a few months later, whereby they argued that the chances of life arising on Mars were about equal to Earth, and we should go back and do a proper study. So the notion of thinking there's vegetation there, or even sending Vikings with landers to try and find microbial life, was all seen as naive, and they said, let's do this properly. Now, the next number of slides coming up are all text, but I'm going to go through a bit of them because I think it's worth it. So basically what happened, as I say, was we decided that we needed to go back to Mars and do a proper study. But this time, do it thoroughly. First of all, ask general questions about the bulk of the planet, and then, its bulk composition, structure, dynamics, internal, the magnetic field. Then analyze on a planetary scale issues such as volcanic and tectonic activity, study the polar regions and understand the evolution over time. Then start trying to understand the mineralogy and the chemistry of the planet. Then try and get more sophisticated to understand particularly volatile materials. You can view the solar system in numerous ways, but one of the most exciting ways to view the solar system is one of a story of volatile materials from Pluto all the way in. And so therefore, when you come to Mars and Earth, the domain of volatile materials is a potential ice, liquid and solid water. And carbon dioxide, again, is gas and liquid. And the thing is that so the volatile materials, the cycling of them through the planet, we want to know about as well. Then start to get more sophisticated by asking questions about water, carbon dioxide, methane, oxygen, the biogenic materials. And then start looking for then the kinds of environments we think might have been on Mars that we think gave rise to life on Earth, hydrothermal vents and so forth. and then plan for specific searches of life. But do it all in that order, and do it in a phased strategy. And again, given this talk is a reminder to me, and it needs NASA scientists in particular and ESA scientists need to be reminded. This phased strategy was proposed in this 1995 document. A huge number of current Mars scientists have forgotten this. Because as you probably know, we want to do a sample return mission, but NASA won't give the budget. And there's no compelling argument coming at NASA as to why, or even as the government, as to why we should do this sample return mission. I hope by the end of this, you will see there's a compelling reason. We keep forgetting it's such a long program. So phase 1 is orbital reconnaissance. That started in 1997 with Mars Global Surveyor. Phase 2 is geochemical landers, Pathfinder, Spirit, Opportunity. Phase 3, exobiological landers, Curiosity and Perseverance. Phase 4 be sample return. Well, that's Perseverance commencing that as well. And phase 5 here in that study was a human mission to Mars for science reasons. Now, the reason why there's validity for this, whether it's cost valid or not, there's a scientific validity at the moment that says that you can do more science using a human on Mars, probably in an afternoon, that you could do in months, maybe years using a robot. That's still true. So, however, we're not there yet, and we won't be there for a long, long time. Orbital reconnaissance. This is then how it was broken down. You break down on a study-by-study basis what you want to do. Geographical, geomorphological, and geological. Elemental and mineralogical. Topographical mapping. Subsurface mapping. Atmospheric isotopic measurements. Magnetic field. And from that then you design the ordering and sequencing of the missions and which instruments are on board. And that's what was done. And that's what's being done now. No Mars mission since 1997 is arbitrary. They're all chained one after the other. We only send to the next one when we have the answers from the previous one and the new questions it has asked. And that's why a sample return mission, for one thing, is compelling, because it's the next logical reason or thing to do to go there. And then if we look at then, did I go through that? Yeah. So you then get down onto the surface and you do the same thing. Surface imaging of to the meter and micrometer level. You then analyze the geography, geomorphology, the actual mineralogy, thermal cameras, you do all of that, isotropic measurements using all sorts of different spectrometers. Then you do molecular analysis down to complex chemistry. And then you actually maybe even consider if the notion of looking maybe for past evidence of fossilized microfossils. But we're not there yet. And even talking about looking at, I mean, it sounds sophisticated looking for cycling of water through the crust. That doesn't get you life. You know, what we're talking about here is a process of understanding the planetary systems that we think gave rise to life on Earth. We don't really know, but we think gave rise to life on Earth. And we want to see, did the same happen on Mars? And then we ask ever more sophisticated questions about the kinds of complex chemistry that might give rise to prebiotic chemistry. And in terms of then the search for life itself, you break it down into a 3-phase process itself. You understand the planet and everything associated with planetary characteristics that would give rise to life. I've listed a lot of those already. Big ones are tectonic, volcanic activity and water environments to give us hydrothermals, that kind of thing. A hydrological cycle, a carbon cycle, these big cyclical systems, you need those. Then we talk about water and atmosphere. Well, I've just mentioned that. What kind of, therefore, evidence would you expect to see? Hydrated materials, precipitated salts on the surface. So they're the kinds of evidence you want to go look for when you go to Mars, and we're finding them, by the way. And finally, then, the notion that there might be some life there, maybe in some sort of extant or dormant state. So where would you go there? The likes of the poles. We've discovered subsurface water recently, subpolar ice cap lakes, briny lakes, maybe in cave, underground, there's a thermal gradient. So we're nowhere near doing those sorts of investigations yet. The actual Rosalind Franklin rover that Europe hopes to send, actually now around 2028, has a 2-meter drill. It will commence some of this work. And again, what are the sort of things you might look for? Stromalitites, mats, reefs, calcium carbonate layers, and then even biomarkers. When you then get down into the actual looking at the organic molecules, that you're finding evidence of amino acids, lipids, phosphates, magnetite and iron sulfide, which are the raw materials, the leftover materials of bacteria. And what sort of sites might you look for there? Ancient thermal springs. And by the way, Perseverance is right at one as we speak. It's just arrived at what we think was an ancient hydrothermal or thermal region. And therefore you look for, iron oxides, ancient lakes and seabeds. Well, we're there on both curiosity and perseverance, and then to look for siliclastic sediments, compacted cemented materials that might retain fossils of bacteria. You could go on and then, I say, the polar regions, the tundra regions, and so forth. So you can see the kind of the lineage of thinking that's been going on, both in Europe and in America, on this since the early 90s. And it's a very strategic, it's a very planned, it's a very thought out process. It's a phased program. And to me, actually, I'm going to do a whistle-stop tour now of some of the results of this. It is one of the great modern science endeavors that we've done, and we're continuing to do. So it started in '97 with Pathfinder arriving at Ayers Vallis, which we thought was basically the flood channel of a giant flood in the past, and this verified it. But this is a test bed mission really to test rover technology. Almost immediately was followed then by phase 1 orbital reconnaissance. Mars Global Surveyor arrived in late '97, Mars Odyssey in 2001, Mars Express from Europe in 2003, and Mars Reconnaissance Orbiter in 2007. 3 are still working. Mars Reconnaissance Orbiter is probably still working. It's just somebody sent a piece of software to it in 2006, knocked it off target, and we've never been able to communicate with it since. But it did extraordinary work. It first of all showed sedimentary layering everywhere on the planet. You don't get sedimentary layering on the moon. You only get sedimentary layering through, sedimentation from wind, water, and so forth. Everywhere on the planet, including sedimentary mountains. Now that was a discovery. Most of the mountains on the moon on Mars are not sedimentary layer down. So this is evidence of possible tectonic activity. River deltas. This is in Holden Crater in the southern region. Magnetometer measured magnetic striations in the crust showing very ancient tectonic movement and reversal of an internal dynamo. Now, this is around 4 billion years ago, very early. The Mars molar map, which again shows that the great dichotomy between north and south, 650 laser pulses, 650 million laser pulses fired at the surface, Mars Reconnaissance Global Surveyor, and with a vertical resolution of 1 meter, horizontal resolution of 100 meters. And there's, for example, Ayers Valley, where Pathfinder is. You see the great flood channels, the Kazai River, Valles Marinaris, the great Tarsus Bulge here. So the dichotomy between north and south, absolutely crystal clear here. Odyssey in 2001 came along. It did amazing mineralogical mapping. So almost within weeks of it being there, it had actually produced this map showing 6 degrees north and south is water. At least the top 1 meter of the regolith is 50% water. It constitutes 5 million cubic kilometers of water ice. We've verified it's there through Phoenix. I'll show you in a minute. Also, precipitated salts in the northern region suggestive of water there in the past. And every color on this map, it's 30-meter resolution, is a different mineral. So mapping the mineralogy of the planet. Mars Reconnaissance Orbiter arrived in 2007. Oh no, this is Mars Express, and gave us kind of lots of 3-dimensional perspectives, as well as radio sounding, which is radar underground. We measure the echo. And so therefore, being able to probe below the polar ice caps. And if you may remember, around 2018, discovered a very briny underwater lake underneath. So that's big. We're talking about the fact that we've got a lake of water now. It's minus 68 degrees centigrade. It's very salty. It's very briny. But nevertheless, one of the big questions about Mars in the past was, could liquid water be supported on the surface? Now, whether it's a low sheet of ice or in a denser atmosphere, we are today on Mars saying that above the crust, there is liquid water. So it's just a big point in that direction. We can put our 3D goggles on now to show you the sort of perspectives. This is just a novel thing. But however, the way to look at these is just look at the image and keep looking around it. Don't really move your head a lot. Just keep looking around the image. And you begin now, they've exaggerated the vertical, but I think 5-fold in this. So these cliffs our mountains aren't as steep as you might think. But nevertheless, when you actually look at Mars in this way, what you're able to do is infer the size of everything and from a 3-dimensional perspective. For example, if it was a channel, how much water flowed in it? If it's a lava deposit, how much lava, literally in cubic kilometers, has it deposited? Here's the rim of Olympus Mons. And you can see it's actually very steep. So again, gives you great perspective as to the three-dimensional aspect of the actual planet. Again, the key to seeing some three-dimensional features here is just keep looking at it, look around it with your eyes, and it just forms more and more three-dimensional perspective as time goes by. It really does work. So this might be novel and nice to see, but it's an indicator of the sophistication of the kinds of science we can do on Mars, because we can infer three-dimensional volumes. That's my alarm telling me I've been talking for half an hour, so I need to get a move on. So we can take our glasses off, and I'm going to move swiftly through actually the remainder of the rover of the orbiters. So in 2007, Mars Reconnaissance Orbiter arrived. Now, this is the granddaddy of them all. It can measure, it can image to 0.5 meter resolution on the surface, but it's got extraordinary. All of these orbiters have what are called thermal cameras with hundreds of filters. Now, they use basically what's called thermal imaging and thermal spectroscopy, and that are infrared spectroscopy, basically what James Webb is doing. So what we're able to do, it's comparative geology or mineralogy. So what we've done on Earth is we've actually looked at every kind of mineral there is, and then we've actually interpreted from different thermal filters what color it will appear in that thermal camera. Then we just turn it on Mars, and if we see the same color, we know we've got the same material. Remember, I'll just go back actually a little bit there to the Themis one. So that one there, that's a thermal image. But the green, it's calibrated so we can tell every material that's on the surface at 30 meter resolution from the color coding. And Mars Global Surveyor or Mars Reconnaissance Orbiter could do it even better. So I'll just give you one or two highlights here. Here in the southern ancient lowlands of Mars, in what's called the Noachian region, is the Eridania Sea. It's an ancient sea that was 4 times the size of the North Sea, to a depth of about 1,500 meters, that we know was absolutely packed with hydrothermal activity. And we haven't gone there yet. We haven't studied any of this yet. This has only been analyzed in the last 5 or 6 years. So this will be a site for future missions to go to, because we think that hydrothermal activity was important to the origin of life. We could be wrong, but that's the lead we're following. That's what we're following with our nose. Of course, then it is these river deltas, and here we have Jezero crater, and was able to use then its thermal cameras to infer the different kinds of materials, including clay materials and carbonates. Now, carbonates can come from precipitation of carbon dioxide out of an atmosphere when it rains, and clay materials form in the presence of water and are seen as important to the origin of life, because certain clay materials are known to be able to polymerize genetic nucleotides like RNA. So this has been a hot topic. This is where Perseverance is right now. In fact, I could just tell you, spent the last 4 years driving up through here, and it's just about arrived here right now. We'll see the journey a bit later on. So there are other orbiters. MAVEN has been able to analyze and literally see the atmosphere disappear. Where's Mars' atmosphere gone? Well, UV light and solar particles and cosmic particles are breaking up the molecules of CO2 and NO2, N2, and then atomic hydrogen, carbon, and oxygen are escaping from the planet. That's literally it, observed by MAVEN. And not only that, but the atmosphere is dynamic. So if I just click this movie here, what it's noticed is that basically on a daily basis, UV light from the sun causes dissociation of the particles. Nitrogen flows downwards from high to low altitudes, depending on its position in relation to the sun, and then forms an oxygen to form nitrogen oxide, which glows. And there it glows. And they're ultraviolet glows. You can't see them with the naked eye. They're as bright as aurora on Earth. That's how. And the thing is that it shows dynamism even in Mars' atmosphere. And we believe maybe a contributory factor to, for example, dust storms. Now, John mentioned the United Arab Emirates. What they have is a little probe called HOPE. Now, go check it out. It's giving global images, and they are nothing short of beautiful. The first image of this talk is one of them. This is another. Now, they're doing a lot of science as well. There's an organization in California called MPAG, which I'm a member of, and I've never contributed anything new ever. I don't even know why I joined. I'm embarrassed. But they coordinate global efforts in Mars exploration so that nobody repeats the same mission twice. And the UAE are a member of MPAG, and so therefore all the instruments that are on their space probe have not been done by ESA or by NASA, so they're contributing new atmospheric measurements is basically what they're doing. But the other space probes are struggle to give Mars images because the cameras are so high resolution, whereas the UAE gives the most remarkable Mars images. They're just beautiful. It's a gorgeous mission. and a tip of the hat to them, because they're not a big country. Okay, they might be wealthy, but they're not a big country. But boy, do they mean business in space, and particularly planetary science. They're big ambitions there. There's another image from them, just beautiful. Now, to get to our then phase 2 campaign, I want to skip quickly through these. I'm taking too slow. So we had Spirit and Opportunity arrive in 2003. Now, where they arrived, sorry, my laser pointer isn't working, I think I need to come out here to show you this actually. So I'll show you where all the rovers are right now. So Spirit arrived here in Gustav Crater. You can see it looks like a river flowing through. It's 140 miles across, 140 kilometers across. We had its sister probe, Opportunity, arrived in Meridani Planum, which we suspected to be an ancient sea. You can see hematite there, which is an iron oxide rust material. Thanks, Ninja. We then have, there's Gale Crater where Curiosity is. And then Jezero Crater is, it's hard to see, it's not that crater, it's just about here at the very tip of Syrtis Major. Now, you'll notice that where we land is always on the boundary between the north and the south. Okay, here's not quite that, but it is actually not far off Cricey Plain. So we're always interested in the dynamic change across the planet from the south to the north. And then InSight landed here in Elysium, which is quite tectonically active. Even there's a lot of fossae here showing tectonic activity in the last couple of million years. So that's where Mars InSight is. It's about 600 kilometers north out there, north of Gale Crater. So this is where we've landed. So this is Gustav Crater, where Spirit landed, and Meridani Planum, where Opportunity landed. Very quickly, because I've been through this before, I don't want to linger on this. Spirit did give us some beautiful views. And again, if you just put your goggles on again for this image here. So this is a view from Columbia Hills at the center of the crater. And again, if you just look around the image, you'll realize again just how mountainous it is. You can see several dust devils in there as well. And it really does give a sense of the hilly terrain that these rovers have to actually traverse. I really feel it's worth downloading this image and looking around it with a pair of these for a long time. It's like looking out a window into Mars. It's one of the best ever. It's beautiful. Just a remarkable image. So, okay, we'll move on from that. Its goal was to try and determine, was that an ancient lake? And sure enough, actually through an accident, a stone got caught in its wheel and its wheel dragged up the hill. It actually scooped away the soil and discovered salts directly under the red dust. Opportunity landed in Meridani Planum, as they say, in a hole in one, and immediately in a tiny little crater, and discovered what we call festoon cross bedding, which you get from shallow flowing water, and then these little blue beads called blueberries, which are the hematite nodules made of iron oxides everywhere. Indeed, Opportunity discovered that Meridani Planum was a sea at least twice in its history for millions of years each time. And it went on a vast journey over 14 years from 2004 to 2018. So it left, so this is Endurance Crater here. What was that, Endeavour, was it? I've got these mixed up actually now. No, Eagle Crater, Endeavour Crater, Endurance Crater and Victoria. That's about 5 kilometers away. As it arrived there in 2007, so is Mars Reconnaissance Orbiter arriving in orbit, and that's an image from Mars Reconnaissance Orbiter. There's the image of the crater from Opportunity, and there's an image of Opportunity from Mars Reconnaissance Orbiter. They were linking the gap from orbital to ground reconnaissance. And then it went between 2007 and 2012 to Endeavour Crater, a 24 kilometer wide crater, which you can see is very eroded from water erosion, and was making groundbreaking science there. This is the journey, the 4 years it took this journey. You could follow it online. All of these rovers can be followed on a daily basis online. They're really worth it. I followed this daily for 4 years. It was really, really interesting. And when it arrived at the edge of the crater, it was about, you can see, by the way, the sophistication of the science. So from orbit, we're getting these images of Mars Reconnaissance Orbiter. It's mapping ahead the journey for the rover, and then the rover would go and then pursue that journey. By then as well, Opportunity was an AI machine. It was a thinking machine. It could do excursions on its own. It was basically going down into a little actually valley called Perseverance Valley. And this is a near infrared image, by the way. It's a beautiful image. I love showing it. It's not what you see with the naked eye, obviously, but it's near infrared. And it had driven about 300 meters down in there when a dust storm hit in 2018 and covered the solar panels, and it shut down. So opportunity is still there, and it had discovered clay materials all along the rim of that crater. It was about to do some of its best science when it shut down. Very quickly, Phoenix landed in 2008 in the tundra regions to check, is that water ice? And look at how flat that surface is. We said the flattest surface in the solar system. Scooped away about 1 or 2 centimeters of dust and found pure water ice underneath. Not only that, but revealed something telling and new. Water droplets on one of the actual legs of the rover, of the lander, suggesting that there was a time during the day where the water was too warm for the water to be ice, and the conditions weren't right for it to sublimate. So it had no choice but to be a liquid. It's called a microclimate. So it's opened up a whole new area of thought about Mars science, which is there may be microclimates where liquid water exists just for parts of the day. That may be all that a particular habitat might need. Moving on. So we discovered basically by the end of these phases that Mars was very clement in its past. Thousands of previous rivers. Very similar kind of activity to what we think was going on in early Earth at the time when life was arising, and that meant continue with the journey. So towards phase 3, to try and analyze more precisely water activity, carbon activity, the specific nature of the climate. And we're not there yet, by the way, we're getting there. And then potential plausible habitats for past life. And then therefore in 2012, we sent Curiosity, an altogether different proposition, 1-ton rover, sent there to Gale Crater, which is there, this crater. It is a 3D rendering from the Nolan map, actually. And it arrived there. Now, when you look at a thermal map of this image, there's the crater there, right? This is called Peace Vallis. So, and then you can see an alluvial fan from that river. That's where we landed Curiosity. But look around here, just nothing but rivers everywhere. So the place was inundated by water activity in its ancient past. So the rover came in here and landed roughly here. And Mount Sharp, the central peak of the crater, is in here. It's again about 145 kilometers wide, so 70 kilometers from here to here. So there's a 3D rendering of the actual crater. This is the movie. So you can see there's that piece, Vallis, an ancient river. This is that's where we wanted to land it. I'm going to actually move this movie on, swirl it around. So I'm going to even move it on further. So as it turns around and looks back out towards the crater, I'll just pause it about there. Oh, sorry, and actually I jumped ahead, but I hope you caught it. I'm not going to stay, but you saw how accurate our 3D modeling from surface was, and we could see now. That's it. Looking there's Peace Vallis and the river flowing right there, and it's in the alluvial fan where it landed. Now, when it looks in the opposite direction, out away from this, it's looking in towards the center of the crater, towards Mount Sharp, and this was its view. Now, Mount Sharp is about where the Mars is. It's looking slightly to the right of it, but amazing terrain. And what we're looking at here is a river. It was an ancient lake, and these mountains weren't caused again by tectonic uplifting, but by erosion. So the lake surface was there, and over billions of years, it's been eroded downwards to reveal then the layering, the sedimentary layering of the lake over time. So it was decided that we need to send, and I'll just actually put an overlay of the distances here. Like you see, it's 16 kilometers away. We'd send the rover up in through there and try and actually then determine what the history of climate change on Mars was and whether there was any evidence for life possibly there. And that's what it's been doing over the last 12 years. It immediately discovered everything to do with past water activity. Mudstones, cemented, rounded stones. Look at the layering there, is absolutely mind-blowing. Like absolutely nothing but layers after layers. Again, compact cement on a dry riverbed. It has a drill, it drilled into stones, and really this is where it made its groundbreaking discoveries. Now I'll just go through 2 or 3 key points on the science of Mars Reconnaissance Orbiter or Curiosity. But the first really important thing it discovered was those mudstones contained complex organic molecules. One of them called Cumberland revealed complex organic molecules. So now we have a lake within which the mudstones within it have organic molecules. Now that doesn't mean they came from or were synthesized on Mars, but it's very interesting. Now the other thing as well is that this rover was able to determine was first of all, actually 2% of the regolith is made of water, has what is moist. So there's moisture everywhere on Mars. We don't have to go to the polar ice caps or to those tundras to get water. We could extract that 2% water for astronaut use. And it's about $10 million a kilogram to get water to Mars. So it might be worth doing. I'm just going to go to the next slide, even though I kind of want to mention something with the methane as well. So the big discovery it made at Gale Crater was that it was a freshwater lake with neutral pH and low salinity. And also it had what's called an oxidation gradient. In other words, it basically had more oxidizing agent. An oxidizing agent is an agent that gives an electron, and in so doing can actually transfer a little bit of energy in what's called a redox reaction. And one of the key things in searching for life, the origins of life, is what we call metastable states, whereby you've got some part of the environment that's not so wild that it will break complexity down, but it will enable a change to occur whereby you get a natural energy transition. So an acid-alkali boundary between two types of water would enable energy to be transferred through electron transfer, or an oxidation difference. And they found that the actual different materials had a different oxidation level. So they found an oxidation gradient with depth in the lake. That's what you find in lakes on Earth that allow microbes to thrive. So in other words, what you have here is a habitable environment to life as we know it. An environment that was a freshwater lake, neutral pH, low salinity, with an oxidation gradient. And also we found quite complex organic molecules in mudstones at the place. Now, again, I'll come back to what I said earlier on. That's nowhere near life, you know? It's a habitable environment, but just because you got an organic molecule or water doesn't give you life. We've got to understand way more about what might have been going on there over the years and over the centuries, even over the eons, to try and understand it. And so even though the seminal work of Mars Cure, that's what it was sent to do, figure out, was that a habitable environment? It is confirmed it was habitable to life as we know it. But it's continuing on. Now, this is an amazing image. And you can see sulfate materials that were deposited. This is during when Mars's climate was actually deteriorating 3 billion years ago. So we can actually see that the actual terrain changes drastically. And so that's what the Mars Curiosity is trying to do now. Drive out there from where the alluvial fan was and drive up into this mountain range. And I'll just try and bring the image here. So there's where it kind of started off. So the outside of the crater's up here. It's driven across that plain, remember that 10-kilometer plain? And it's trying to drive up into this called Gadis Valley to try and get up towards those. So in fact, it actually has reached the sulfate materials. It found pure sulfur, actually, which is extraordinary as well. And that's only now. Now, they think it'll probably end its life there, won't make all the way up Mount Sharp. But nevertheless, the point, so we'll come back to this, which was the point at the beginning of the talk, was that look at the complexity of the questions we've asked about the chemistry on Mars, water on Mars, and we're slowly piecing it together. Again, this point that there won't be a eureka moment. We're just building up layer by layer an understanding of Mars and what it was as a planet with similar processes to Earth at the time when Earth was giving rise to life. Now, I'm going to skip on because I'm taking on time. I just have to mention, of course, InSight, because what InSight has discovered in the last couple of weeks was that underneath, it's basically, InSight was an amazing instrument. I've got to show this. So it landed in the Elysium region, somewhere around here, and it had on board a French designed and built seismometer called an inverted pendulum seismometer. They spent 20 years designing it. They wanted to push 12 of them on Mars in the late 90s in a mission called Netlander, and they couldn't afford it. So they gave it to NASA. It's a single seismometer, but it can measure directionality with an accuracy of 10 degrees. And it can measure a vibration narrower than the width of a hydrogen atom on the surface. Now, when Phobos passes over by, it causes tides of 1 millimeter tides. But that's 10 to the power of 7 times greater than it's capable of sensitivity. So it can, and not only can it measure the vibration of Phobos when it's passing over by, but it can use the vibrations as echoes down into the crust and actually use that as seismic information to tell it about underneath. Not only that, it could even use the dust devils that pass by or the winds of Mars to measure down to several hundred kilometers below the surface. So it's the science of this probe are only being poured over right now. The big question about Mars, of course, is why did it cool down? And actually the sense is that we're picking up although I can't get a complete picture on it. Mars scientists are very, very guarded with the results until they publish, by the way, is that it just looks like we kind of thought that Mars might have a thick crust and that it still might be very warm in there, and that we get heat from a system through convection when we get convective flows. Well, of course, if you've got a lid on something and you don't get a convective flow, you'll just retain your heat in there, something superheated. We thought Mars might be like that. No, it just turns out it's just all a little bit cool and cold, even its core. They think it's got kind of got liquefying agents that actually didn't. So that's telling me of 5 minutes ago. Could I take 5 or 10 more minutes? I know it's a long talk, but I've got to get to the best images yet. I'm spending too long on this. But in any case, despite the fact that it hasn't been able to do some of its seminal work because one of its 3 instruments didn't work, an instrument called HP cubed, nevertheless, it was able to use its seismic measurements to determine that there's enough, it found a reservoir of water directly underneath, that if you extrapolate across the entire planet, tells us there are subsurface reservoirs of liquid water under the surface of Mars now, that if you brought them to the surface would fill the entire globe to a depth of hundreds of meters. And that's a constitutes about 10% of Mars's last water. Now, we didn't know that up until a few weeks ago. And that tells you again how little we know about the planet. So the last stage of where we're at is Perseverance. Landed in 2021 while we're all in lockdown. And basically Mars Curiosity on steroids. Lower down with a sky crane, bringing in a little helicopter called Ingenuity. It's got a fantastic laser spectrometer on board and to deposit canisters on the surface for collection later on when it's done all that. Only thing I'll mention about this instrument is, unlike Mars Curiosity, where all its instruments were in the body of the instrument, all its main science instruments are on the end of the arm in a package called Sherlock. But in particular, there's a particular instrument there called a Raman spectrometer, which was a miracle to get such a sophisticated spectrometer on board. What a Raman spectrometer can do is it can actually measure the properties of complex molecular bonds that really are not understandable by any other device. So it may be able to determine whether some of the organic molecules are biogenic, as in were created by biological capabilities. Although I just read something recently where they kind of said no, they think it's still going to have to bring samples home to make that definitive answer. But the results from Perseverance here are really intriguing. So where did we send it? The Jezero crater, just at the tip of Syrtis Major, observed, of course, by Huygens in 1658, I think it was. Now, I love this image because here's Syrtis Major from Mars Global Surveyor, Mars Reconnaissance Orbiter. So it's a very high resolution image. Now, here's Jezero crater, just this innocent crater. Now, even at that resolution, there's nothing we can see that's really interesting about that crater. But you have to go in even further, and then all of you suddenly you see a river delta, a river and a river delta. And I keep forgetting the name of this. They keep naming these things as they go along, and I keep forgetting the name. So I want to tell you the name of that. This little river. It's called the Neretva Vallis. So remember that name because it's about there now. So this is 45 kilometers across. It's not the biggest crater. It's about the size of Dublin Bay, and the river delta area there is probably about the size of the Phoenix Park, several kilometers in all directions. So the objective was to land it there, drive across, go down here. Oh yeah, by the way, this is an image of what it might have looked like in the past, filled as a lake, billions of years ago. So here was the plan: to land it here, to drive up onto the delta, collect samples, drive back down here and go across. Because of where it landed and other reasons, it just could have crossed straight there. But here's some of the images of it coming in. So from the actual cruise phase that brought it to Mars, when it released the probe into the atmosphere, it took a photograph and sent it back to us live at the time. There's the actual delta down there. And then Mars Reconnaissance Orbiter was monitoring it from orbit. So there it is coming in to land on the delta region. Then the actual sky crane took a photograph of the rover. The rover took a photograph of the sky crane. All done. There's movies of this, all wonderfully done. Now, it landed 2 kilometers from the target area in the middle of the, well, not middle of the crater, but further in the crater. But to show some perspective here, like the orbital, the landing ellipse of Pathfinder was 124 by 40 kilometers. By Phoenix and Insight, we got better. Curiosity, we could land it somewhere in a 20-kilometer circle. Now we're down to 4 by 7 kilometer circle. So we're getting better at landing things on Mars all the time. And of course, once it landed, it took some images. And really, I just want to kind of give you a quick pictorial view of what it's done, and then we'll talk a little bit about its results. So of course I had to traverse across here, and that's what cut this piece out here. So you can see all this online. You can follow its journey on a day-to-day basis. This is directly just screenshots of my computer of the actual journey. So for the past 4 years, again, while we've been in lockdown and trying to get ourselves out of the pandemic, it was traveling here. So basically a four-phase campaign of 1 year in the crater floor, 1 year at the front of the delta, 1 year along the delta, that's 3 years, and about a half a year coming up through Vera Vallis, and then this is where it's kind of around. In fact, a bit further on, it's about here now. So it's done that journey. And the NASA were releasing the images through Facebook every day. You could follow it again. Just wonderful. Again, I'm just showing a bit more detail to show the number of stops. So these, might travel 100 meters a day and do some analysis and then continue on. And say this is where it is now. So the thing is that to just show you some of the images, and then say we'll talk a little bit about the science and the consequences of it. So it's looking. So the river delta will be about out here where my pen is. We're looking at the crater rim, but beyond the delta, I suppose, to its left. If we look further into the crater, in fact, I kind of wanted to highlight this earlier. If I go back to the image of the crater stuff. So this, I think it's this feature, there's several of them, but anyway, it's looking in this direction, and there we go. That's it there. And another image of in the crater. And then around 2022, oh yeah, I should mention, of course, Ingenuity. So this is a little artificially intelligent helicopter. Even though the atmosphere is only 1% as dense, actually the revs, I can't remember, I think it's 2,400 revs per minute. It's not that fast. You don't need crazy revs to get a helicopter working on Mars. So the little guy, basically thinks it's a little movie, was supposed to do 4. It did 90 flights. So this is just a little demonstration of it. I think that might even be its first one, showing itself go up and down. Again, I just got actually a 3D one day, and the 3D one, if you want to take a look, just to show you actually again the terrain. We're nearly there, guys. So, and again, you got to just keep looking at this because it is color, but you just get a sense of what the sort of terrain that these devices have to terrain. You can see it's layer after layer after layer. Again, the key is just look around the image, keep looking at different parts of it, and the longer you look, the more the 3D perspective comes clearer. So not flat as you might think at first. So I'll just move on. I'll just mention in passing, we can keep your goggles on for this when you want, but it's called Wildcat Ridge. Now, this was an important location for samples. Basically, we found organic molecules in samples here. In fact, I can say that of all of the samples, I'll move on. Of all of the samples that Perseverance has taken, there's organic material in them all. Now, this is a beautiful view right down into the valley or into the crater as it arrived at the river delta. Now, one of the things I never liked the Martian movie about was I always felt that the actual scenes it showed were too spectacular looking. Well, I have to say, I think this matches them. It's absolutely stunning. Now, when it went up into the river delta then through 2022, 2023, you can see that the terrain is altogether different. Very bumpy and with an awful lot of actually loose deposits there. So again, it made a number of collections, a number of analyses, and has laid a number of capsules on the ground as it traversed the river delta. Now, there's a high-resolution image of this version of this image you can get. I have it on my computer, but it's a gigabyte. And even this computer, doing my head, it's got 8 processors, and I've got 64 gigs of RAM and 2 terabyte solid-state drive, and I couldn't handle a 1 gig image. What the hell? That's Mac OS feed, isn't it? Crap. But anyway, the thing is that these canisters, there's a high-res image of this particular image, and you can zoom back and you can see about 10 of the canisters in the distance. And in fact, you can go on again the web and find out where are all the canisters, where are they laid down, about 10 around there, all the way through them as it traversed the 4-year journey. 25 have been laid. It can do 43. I chose this one here, 24, because look at it, silica cemented carbonates. If there are microfossils on Mars, they're in that capsule. Because that's where we said earlier on is where we would think that's the most plausible place in a kind of an ancient lake setting, in a cemented carbonate, silica-based carbonate is where we would like to look. I don't believe there are, by the way. I think it's hard to know. I'll be just done now in 1 or 2 more minutes. But however, that's not really the point. The point is, again, I hope I'm driving you nuts and saying over and over again is that the point isn't for a eureka moment. The point is, look at what we're doing. Look at what we are doing. It's blown my mind just even preparing this talk. we have a rover at a place on Mars that we determined from orbit was a freshwater lake 3.5 billion years ago. And we're driving to precise locations where the clay materials and the carbonates and the silicates are with an AI-based robot that's already sampled the materials, given us a preliminary analysis, and has laid 25 of the counters on the ground ready to be picked up. Is sample return the next step? Absolutely it is. So just to show you a few more images to finish off, there's an image from the actual helicopter of the rover. Again, it seems as if steering it and directing it has been a challenge, although it's autonomous actually because of the delay. Here's an image of that Nedvera Vallis coming out. So now this is a lovely final sequence which I've been following since May on Facebook. So we're looking down. If we can just go back a few. We go back a few. Sorry, guys. We're looking down this, and we're heading up here. So that's the Nedvera. Let me get the pronunciation right. Neretva, not Neretva Vallis. Let me go forward. So we're looking down Neretva Vallis, and as you may have been, if you've been following it, found Ingenuity did its 90-something trip, but it broke one of its wings, so it can't fly anymore, and that's where it's staying forevermore, on that little water channel in Jezero Crater. There it is. So this is now the rover on its way out of the crater up the rim, and it's got a very steep journey again. This is Neretva Vallis. That's the back. Look in the back of the rover. There is the Neretva Vallis. Now it's looking forward. It's got a very steep climb. It's done the steepest climbs ever done by any rover, 300 meters each, right? And you'd think it was going to do it. There it is, looking back down again, looking forward and up and out of the valley again. And this is then as a 3D map. So this is where Ingenuity landed. This is where Perseverance was when this was made. You'd think it would go up there, wouldn't you? No, they actually drove it up here because this is where this hydrothermal vent was, which again, the name is called, it's a beautiful name, Pico Turquino. They think was ancient hydrothermal was going to say activity, and they've just sampled it. It's only been there in the last few weeks. They've taken the samples there, so again, be a year or two before we actually get the results there from there. Well, I could go on. Well, I'll just go on and briefly mention, of course, the war with Ukraine has scuppered our European rover, the Rosalind Franklin rover, which was supposed to be there already from last year, but earlier this year, actually, was it June this year? 23 or 24, can't remember. But in any case, NASA are going to bring it there in 2028. It's going to go to actually not for the Chrysea, Phoenicia, there's tons of carbonates and clay materials. So they're going to bring it to there, not a million miles from where Viking 1 is, or where Pathfinder is, somewhere there. And it's going to drill down under the surface. That's crucial, because what we're realizing is that the redness is skin deep. So then the next step, of course, is sample return. And we thought that was happening. Not only did we think it was happening, but ESA have signed a contract with Airbus to build the return orbiter, which is 60 meters wide from solar panels. And NASA were then supposed to build the next lander and rover to collect the samples, put them on the Mars Ascent Vehicle, put them in orbit, and then in a little kind of basketball-shaped object, then the European orbiter would collect it and bring it back to Earth by 2031. But they did a cost analysis. Now, NASA stupidly offered to say to Europe, don't bother with them. I think it was Europe was to build a rover, and NASA was to build a MAV. And then NASA said to Europe, don't bother building the rover. We'll do another thing. We'll maybe use another helicopter. Now, of course, in the quagmire of the whole thing, the design has been changing. And then they did a cost analysis earlier this year and realized it would cost about $10 or $11 billion to do it, rather than the projected $3, $4, $5 billion. And so we don't know where we're at with it. And scientists are struggling to convince NASA to do it. It is a lot of money. But the thing is that, however, not only is it the next logical step in terms of Mars science, because the samples that Perseverance have collected are truly as good as it's going to get. But secondly, if you want to send people there, which is decades away, by the way, no doubt about it, you still never need to test the notion of getting to Mars and back. And that was the logical next step, was to build that kind of technology. That's not done yet. We're not there yet, but it is actually kind of not. When I gave this talk even a year ago, I was thinking it's going to happen. Now, it's far from clear as to whether it's going to happen or not. And I think all of us in our own capacity should be encouraging our local TDs or Enterprise Ireland, whoever it is, think about Europe maybe stepping up to the plate a little bit more and offering a little bit more on this if they can, because it is a really, really worthwhile next step. Now, I'll finish on this. I have to say a few things about humans on Mars. We don't have the time. You're all dead. Or I'll tell you there. You're holding straight. But anyway, the thing is that what I want to just finish off on is I hope I've demonstrated the sophistication of this program. It's a multi-decadal program, and the actual the consequences, I suppose, are important, because if we get to the holy grail of answering questions about origins, you know, that's going to be of profound consequences to science. Now, I often say that going looking for life on Mars is always the wrong look. You could go to 1,000 locations, even if life is there, and not find it. The point is that this is people doing really good science, ever better. And we are getting really, really good at this. It's an amazing test bed for our questions on science, on questions of origins, and how to explore planets. We're so lucky to have this planet as our next door neighbor. It's not to say there aren't other important targets and priorities for budgets and all the rest of it. But nevertheless, I'll just leave you on these final 2 points. Number one, if we were to discover microbial life there, it would be a seriously important discovery, because it would, first of all, be a second take on biology. And that would even have biotech consequences. A second analysis on a genetic evolution might generalize biology for us. And secondly, there would be very, very big interest from biotech companies. And the notion, for example, that a company like SpaceX might discover it and then retain it as trade secret is a question that we got to consider, because they have intentions to go towards Mars. But secondly, I personally think that we don't know Mars very well. What we're realizing is it's an incredibly complex, changing, dynamic world with its own natural history still to play out. It has vast reservoirs of water. If we weren't around, Mars would become a watery world in 1 billion years when the sun heats up. And if there's any life there or potential for life there, it might arise. So its fate is in our hands. And I think we need to think about that. And I actually think, and this is something I want to do, if I can never get my decade-and-a-half-old PhD off my back, if anyone knows, he knows I'm doing a PhD forever. I really want to get my PhD done because I want to get involved in this somehow. I don't know how, but I don't want to rush people to Mars. I want us, actually, I think we're at a stage where we need to say, we need to reappraise this planet and what its value is to humanity. Because again, I'll just take a step back. Look at what we're doing. We're on a planet like that is just a variation on the theme of Earth. It's so familiar. The volatile cycles, the water cycles, not one exoplanet we've discovered of the 5,000 is remotely like Mars. If we discovered a Mars around another sun, that will be headline news. And yet here we are exploring one that's on our cosmic doorstep. And for all those reasons, it is a cosmic stepping stone in terms of our next steps into space. Thanks a million.
Thank you very much.
Well, again, my apologies for going on for over an hour. I tried so hard to keep it down.
Well, it's fascinating. Sure, you all agree. And in fact, when Kevin mentioned SpaceX, there was a firework went off outside. There was what SpaceX and unplanned construction event. But speaking of exploration over time, I know Kevin's book is still available on Amazon if anyone is interested.
Well, it's only half the story now. Actually, I pride myself, and I wrote it in 2008 about this, but it describes all of the early science and the structuring of the phase program, the instruments we use, and it gets a spirit and opportunity, but doesn't get your curiosity or perseverance.
And who's also here tonight, Brian Harvey's books are available on Amazon.
Brian Harvey's an amazing science author. He's written 19 stunning books. Check out And the latest one on Japan and space, I just reviewed for Astronomy Ireland magazine.
And when you mentioned the sample return, obviously here, like of course, is Japan planning the Phobos sample?
Sorry?
Is Japan planning a Phobos sample return
Oh.
or in conjunction or?
Oh, yes, you're right. Yeah.
There is a planned sample return.
From the moon of Mars, Phobos, which is an altogether different thing,
Yes.
but it will demonstrate return technology. Yeah.
Yes.
Yeah. So
But I'd like to invite anyone that has any questions. Well, Terry.
Thanks, absolutely fascinating and truly amazing images. Just one thing you have to know, the seasons on Mars, according to all the official sources, begin and end at the equinoxes of solstices.
okay, I hear you. We've been debating this.
That's a really thing between
No.
everything.
Yeah.
If the surface has not been majorly reconstructed due to tectonic movements, there must be some very old features on the surface, which you can date approximately from the rate of meteorite impact.
Yeah.
What is the oldest feature on Mars that we know about, and what does it tell us about the very early history of
Right.
Mars?
Well, in fact, that sea, the Eridania Sea, is part of the oldest, really oldest part, because in fact, it's sitting on some of those magnetic striations, which we know only happened for a few 100 million years at 4 billion years. So what it's telling us is that, like, this is the thing we forget about Earth was when life was forming on Earth, there were craters on Earth. And even when I wrote my book, I always looked at the southern part of Mars thinking it's the most alien moon-like, and that the northern smooth parts of the most are like, no. So it's that northern lowlands is the most interesting from the question of origins. And it's the hardest to get to because it's so mountainous, and why we haven't gone there. So what we're finding when we map the Noation period, so there were three great eras, as you know, in Mars history: the Noation period from 4 billion to 3.5 billion years ago, then the Hesperian period from 3.5 to about 3 billion years ago, where it cooled down as a planet. So all of the lava plains are more recent, 2 billion years old. That ancient area is the actual impact region. And there's two big questions. You do hit on two big things, Terry. Number one, the indigenous nature of that Noation period is why we want to go to that Eridani Sea to find out what water activity was going on. What are the clays? What are the sulfate? You know, is there evidence of prebiotic activity in what they think? Like, they think they've spotted hundreds of hydrothermal vents in that sea, hydrothermal vents that were at a depth of 1,500 meters. But the other great question about Mars was, which I've never really kept actually that much abreast of, is the Hellas Basin. Because clearly we often kind of think, oh, just cool down because it's slower. No, something hit the bloody planet hard around in the late bombardment. Hellas is it. And then that may have even caused that lava flows over the north and just basically change the whole direction of the planet in one go. So we want to go, it's not even that we want to go down to the southern lowlands and find out what's the crust made of there. We want to know what really happened on Mars 4 billion years ago that may have been a major contributor to steering its direction. So they're two big questions. But you're right, this target, it's called the Noation period, where that Eridani Sea was. It's kind of halfway between the Hellas Basin and the Argyre Sea. That mountain is the most interesting region. And we're only now beginning to build the landing technology with Perseverance capable of landing somewhere where it won't upend when it lands. That's the best.
Because as you know, the Martian orbital temperature is slightly more than that of Earth. And I think possibly the reason for the Earth's orbital temp was the impact that caused the Earth-Moon system. So if something similar happened to Mars to go with an even greater orbital temp, would there be a sign of a major impact crater? Or Hellas probably wouldn't be big enough, would it?
I don't know actually the answer to that. Yeah. I mean, it does, Mars does tilt a lot. It's at 24 now, but it can tilt as far as 60. So it's just at the behest of its own angular momentum changes basically.
Yeah.
So I don't even know whether or not we'd know at what, orientation what I suppose the only thing you can say is they're the ancient lowland. So if it but that's a complex question actually you're asking there. Yeah.
Thanks very much.
Yeah. Well, no, Terry's heard this talk before. I was very grateful you sat through it.
You've updated
Yeah, well,
quite a
well
bit.
thank you for sitting through it.
I think I've told you I studied the Balkans before and Eastern Europe before, so the direct valley is a big valley canyon in the middle of Bosnia. That's where it gets its name from as well.
Right.
And you'll zero these lake and a lot of Bosnia or East European language as well. So
Okay.
don't be sorry, you have all of that was the same Bosnia for that too. That's one point.
Thank you.
Second point about just more serious those about the measuring Mars quakes as well, and the S&P waves and refracting to the surface as well, refracting as well through to the like is there Martian comes up more Robert's continuity. where they have a boundary between the crust and the mantle as well through the time. And both the S&P waves given up
Yeah.
by the landers be able to detect how far down the mantle is, instead what
Yeah.
they call the water-bearing rocks
Yeah.
would end,
Yeah.
things like that too.
So the question is really about the boundaries of the planet interior. Yeah. Those results are only coming out now, and I don't think you'll get definitive answers, and this is not fobbing you off. But however, the whole point about the seismometer was to actually determine the internal structure. What we do know is that the crust is thinner than they thought. The core is bigger. It's actually, and it's more liquidy. So that, and they think that's how it just kind of cooled down, that it was just kind of just greater convective dissipation of the heat over time. On Earth, there's 2 layers of mantle. And that's what gives rise to the dynamo. And they think that they're kind of more mixed. This is where I haven't got the latest information on this yet, but it looks like it's a bit of a mess between the core and the lithosphere. And they're trying to figure out that, to try and understand it. Now, the reason why this is so important is it's great to talk about the surface of the planet, but really we need to know about the bulk, structure, and behavior of the planet and evolution over time to get back even to these questions to find out what's going on. And actually, even the question might be, is there some sort of evidence of a serious impact that's actually embedded within the actual planet itself, or emboldened within it?
Might be a serious problem in the future, like for possible future mandate.
Well, actually, first of all, getting Mars quakes of greater than 4. They only, I think, detected 1 in the 2 years that it was actually active. There's lots of Mars quakes, but they're all quite small.